Okay, this handbook, it was underwritten by the IGS. Make no doubt about it. There was sponsorship behind it. It needed to be concise. It is not meant to be a very large document, so it needed to be concise. It needed to be generic. We don't want to offend each other, in this, so it goes across the lines of things. We think it should be an essential resource, not just for engineers, but for the general public. So this is important in that regard, to make it very easy to read. I won't say you will put it on your nightstand, but you will. It's a joy, it's a pleasure to read. It's a living document. The next revision is already in the works. So this document will not stay static. It's expected to grow over time, which is neat. This is very important, and I will circle back to this in the big picture of things. Geosynthetics do not stand alone. They stand inside of a system, a quality system. It's not just a good manufactured material, but it's how it's installed. There's operations and maintenance associated with it. So there's really a system approach to using geosynthetics, and hopefully this book circled around to this. Vim was very kind. He said, my name's on the cover, but there's a debt of gratitude for me for people that participated in this. I will go through the entire handbook in 45 minutes, but the chapters are written. It's an introduction. Roadways by Eli Coelho. Barry Christopher for subsurface drainage. Erosion control was Joel Sprague. Chris Lawson for reinforcement. Kent is in the room for seepage control. And it's always nice to end with a night. So Professor Kerry Rowe finished the thing. So it's rather comprehensive as well as geosynthetics is concerned. The definition of geosynthetics, look at it in 3 parts. It's a polymeric material used in geotechnical applications, soil, rock, and to make structures. So look at those 3 items and think of the definition, what we're trying to cover. I love history. Everybody says that this is not an old history. The international conference was held in Den Haag in 1990. This was only the 3rd of the conferences. So it's at the 13th now. But it started with simulating natural materials, leather and rubber in particular. Okay? Look what's in red up there. Preciously few polymeric materials are being used here. The first of which is PVC. Then you march into the olefins, relatively new technology. Okay? The first applications of this material used in the late 50s, early 60s. Okay? And the first international conference was in Paris in 77. So this gives you a relatively new history. It's almost exactly my lifetime. So maybe it's 65 years tops. The applications are many and growing. This is not a stagnant technology. And I like to see the students because there's a lot more to do. There's a home for you here. And we're just starting as far as the invention is concerned. The textiles were the oldest of them, used as filtration, also as reinforcement, separation of materials. You see a bunch of different applications here. Reinforcement, think of steel to concrete, geosynthetics to soil, okay? Providing that tensile reinforcement in the material and also can give confinement. So you can make, out of nothing, you can build on it. In the definition you saw, planar. I discussed outside, this might not be the case. The 3 dimensions comes to you quite readily now with both drainage applications as well as cells. So you can make a 3rd dimension out of this and go well beyond being planar materials. Drainage materials, the efficiency of geosynthetics is orders of magnitude greater than natural materials. So coupling the natural materials with the geosynthetics becomes quite powerful. Barrier materials comes in multi-forms, can be polymeric, can be bituminous, can be clay in the form of a GCL. So you have many alternatives. You can make composites out of this and really expand your horizons as far as containing both water and waste. The pipe business. How big is the geosynthetic business? The planar materials, arguably $7 to $8 billion annually worldwide. If you add plastic pipe into it, it's another $40 billion. So that's why there's an argument of not adding plastic pipe to it, but it dwarfs the planar materials. Erosion control, a very big concern. The 2 applications, one being channels and ditches, the second being slopes. Foam, urethane, styrene, and glass, all lightweight fill, particularly nicely used with reinforcement to give you an added benefit from it. Okay, now we move into the text. I see some of you have it. You can thumb right along with me. Geosynthetics, we parse them into types, starting with textiles, grids. It's terrible. The manufacturers patent geostraps, so we have to call them geostrips. It's a reinforcement. It's amazing. Cells, nets, membranes, GCLs, bituminous, cementatious composite materials, plastic pipe, erosion control, foam, geocomposites, the marriage of 2 of those together, and then appurtenance is how do you connect these things? Okay? Now the superposition of those types against functions. And my father has been passed almost 10 years now, but this is sacrilege for him. This is his son. He would not move into this many functions, okay? But I think it's necessary. So you really expand your horizons into some of these, and some of them are quite exotic. Diffusion of the material, conductivity versus resistance of the material. These are niche areas, but certainly very prevalent in what we do. Now the thing is to marry those 2. It doesn't take much. A lot of you are engineers, but this superposition of those types versus the functions. It might not be a primary function, but it could be a secondary or tertiary function that these materials supply. But that's what the first chapter does. It sets the stage for these subsequent chapters to move along and progress. The first one is in roads, and this is Eli Coelho. And he works for TRI Environmental in their South Carolina office, does a lot of work with AASHTO. There has been a complaint with this document that it's too U.S.-centric. I apologize, but that's where we're from, sort of thing. I can imagine it will broaden from this and get a much more international flavor going forward. Eli breaks it down into the benefits, roadways. You'll have a second presentation today on roads, so I won't dwell too much on this. I'll just the functions, and then road applications, performance, and then a little bit on railroad applications as well. This is arguably the biggest use of geosynthetics in the world. You see it here on an international flavor. We say low-hanging fruit. This is where a lot of concentration for many manufacturers are just because of the size of the market, and it's growing considerably. I talked to you about unpaved roads, and this is the less sophisticated application that's out there. This was the start of the material. It can function really in three ways in this application: as a separator, stabilizer, and reinforcement. The big reason for this is technical. Okay? You have an order of magnitude increase when you shift this from punching to general shear. The geosynthetic will do that when it's incorporated properly with the reinforcement. It will turn a CBR 1-2 material and jump it up, over to an acceptable or buildable roadway area. What I mean by this is by these photographs, you can see the actual installer, the foot going through the textile. If it was drawn taut and aggregate was placed over top of it, you would change that to a general shear failure. You see the rutting in the roadway. This is what we're trying to eliminate with just the geosynthetic and soil, or soil and gravel. The work was originally done, this is the original work from Giroux and Laurier. It's now been changed by Ji Han, to extend the work, but the reinforcement will behave to strengthen and also to stop lateral spreading. But it's changing the mode of failure in this unpaved road. You will need the tensile capacity of the geosynthetic, and this is typically done by a wide width tensile test. This is done in two avenues. One, the ISO technique, and the second, the ASTM technique. The key element to this, though, is the modulus, the initial portion of the curve. It's done at lower strengths, and it's helped out tremendously in the stiffness capacity. The Giroux has very nice tables associated with it, and what you're looking at is the increase by the addition of the geosynthetic. We're building on water. I feel humbled saying it to you here, though, because you know this. This is your land. This is where you made your hallmark. All of it is flat land, and there's not a good piece of rock around. So, thank you for tolerating me. You see the rationale for this, and the rationale for this is directly targeted for benefit cost. Okay. You see the example problem that was given to you. You save 100 millimeters of aggregate. What does that cost? The cost associated with that is location. How far are you from the quarry? Traveling. What is the savings, though? And Kent and Henning will talk about it later on, about sustainability, keeping the trucks off of the road. Particularly in congested areas. This is tremendous benefit and comes into the circular economy that Wim will talk about later on. This is the primitive part of roads. I have only 45 minutes, so I can't tell you, but geosynthetics are also used in paved roads. They're used as separators between the subgrade and the base course. They're used inside the base course for reinforcement and lateral deformation. They're also, the biggest application, particularly in the US, is in the pavement structure itself, particularly with asphalt overlays. So big applications as bond breakers in that role, but tremendous use of materials and probably the biggest usage of geosynthetics. Moving on, the next chapter was Dr. Barry Christopher, and he talked about drainage and drainage applications. This is a big branch, and it goes right with the TC, so with inside ISO or IGS. They have specialty conferences associated with this, and drainage is particularly one of them. Barry breaks it down into the different applications, structural drainage, dewatering, and then detention. But this is, I'll show to you two major applications here. The first, consolidation, and then the second one in regards to landfills with both a leak detection and leachate collection and removal system. The first one is, it's wonderful. It replaced the technology of sand drains, which was difficult to construct, and it made, it's not a real word, but doable, constructible. It made it a possibility to expand our horizons considerably. The application typically takes a 100-millimeter core and encases that with a geotextile. The geotextile is acting as a filter separator. The core itself is acting as a drain. When you see it installed, it looks like a sewing machine. Okay? I've seen these things as tall as 50 meters. They're on huge cranes. And I've also seen them on barges where they're being deployed off of barges in water. They're sticking them down so quick, you hardly worry if you're witnessing it. No resistance with the wick going into the drain. A sand layer above it or a drainage layer above it to apply the normal pressure and push the the water into the drains and out. There is no wicking going on. Prefabricated vertical drains. Very little of this has a wicking element. I said that in a conference in the UK, and Nigel Wrigley said there are people making osmotic ones. So it's interesting that don't limit anything as far as geosynthetics are concerned. What you're looking at for this is the time for consolidation. The theory is very well understood, and the element that you're worried about, that you're trying to modulate, is that H. Okay, that drainage path length. So how close is the spacing of this, and the attribute of that is again well understood. Cutting that drainage length will shorten the time for consolidation. The next application is typically in landfills, and very different technology between the U.S. and the rest of the world. The U.S. mandates that there are double composite liner systems. Going from the top down is a leachate collection and removal system to reduce the head on the liner. And in between the two liner systems, made up of a geomembrane and a clay, is a detection or witness zone. Okay? Think of it as a lysimeter underneath the primary liner system. So you have this for you, and how is it installed? You see it. The composite materials are almost never used on the base of the landfill. They are used on the side slopes, though. On the base of the landfill is typically a heavy needle punch nonwoven protecting the geomembrane, and then aggregate interspersed with a herringbone of plastic pipe. Okay? This is so that you can build tremendous height and utilize the land space. On the side slope, though, is a composite material. Okay? This is it in all its glory. You can see the composite. We never leave it exposed for long. These are long longitudinal cells that are built quite quickly. The connections, how these are terminated, are extremely important for the long-term proficiency of the sample. Again, you do not want that 300 millimeter net to be exposed to fine particles. You can imagine if that migrates down to the sump, it'll ruin your system. Okay? So the system has to be installed quickly and cleanly. How is this working? Do you believe? If I had a geosynthetic with me, a lot of the public would be very questionable about this 250, 300 millimeter net. In the U.S., it's not done off of trust me. It's done after, science, after measuring. This is a state in the U.S., New York. Every municipal solid waste facility is double-lined facility, each dot there. And they have to report publicly what their leachate collection and removal system is monitoring and also what their detection system is monitoring. And it's reported publicly on the internet. And this is the results. And I submit to you, we are not perfect. Okay? These systems are reducing the head on the primary liner system, but there is something being detected in the detection system to the tune of 70 liters per hectare per day. Okay? That still has a composite liner system underneath it, and it's about 99% efficiency. Okay? I'll get to this at the end of the presentation to show you the summation of it or reasons why this occurs. But there's still room for improvement, and certainly we are improving over time with that quality system approach. Okay, moving on, Joel Sprague is the next section of it. And he's in regards to erosion control materials. He gives applications. Is this a temporary or long-term application? Some of these erosion control is just to have vegetation, so less than a year. The next time increment seems to be about 3 years, and then it goes into long-term applications. But it's nicely done, the chapter. Rolled erosion control products, long-term applications. Then he goes into synthetic turf, cellular confinement, geocells. Anchoring these systems is important. Cementatious materials with the GCCMs. And then he goes into geotextiles, fabric forms, and things along that line. Let's talk about erosion control. It starts with either wind or rain, and you have detachment of the soil particles. Then transportation, typically down gradient. Subsequently deposition. And this figure by Tyson I love. This is the velocity of either water or air and how those three phenomenon are superimposed on this size of the particle. Much more erosion with fine-grained particles, loose and silty materials in that regard. You have two applications, as I said. The first is channels, ditches, and the second of which are slopes. Let's look at the channels and ditches. This settlement is what's worried, and particularly to aquatic living items. It's controlled by the velocity. Okay, very much the velocity is the key player in this. And you have test results on long-term performance versus flow duration. So if the duration is high, but for a short period, it's much different than if it's over a long period where you have the detachment. The stacking of this, everywhere from hard armor down to bare soil. The control is typically bare soil of a known mass. It was fascinating to walk into your laboratory. What a privilege to walk through it. But just you know the soils and you see where we're coming from. The next is slopes. Slopes, particularly when they get steeper than 3 to 1, become problematic, and you need to obstruct this for vegetation. They are test methods for this as well, rainfall simulators on known slopes, but it works out nicely. The key factor for this in this is the erodibility factor, and it's controlled by the soil loss equation. Different specifications are made based on this test method, but the soil loss is pointed out by Joel in the title of it, and a plethora of materials are available. They typically are three-dimensional materials and work quite nicely in this regard. Installation Joel goes into, and how important it is to anchor the material as well as to have the correct overlapping and fixity of the material. You cannot bridge a gully and anticipate this to work correctly. There are layout diagrams or guidance from this. The handbook shows those and at least gives you the avenue of where to go. If you would hand this to a contractor, they would know where to pursue this going forward. Okay. I have children. I'm not supposed to pick a favorite, yes? This is my favorite chapter. This is a gentleman. Chris Lawson of Tenkata hit the ball out of the park. It is beautifully written and very explainable from the perspective of reinforcement. My hat's off to him. Kent's here. I don't mean to offend you. He's my family friend. But this is just beautifully done, this chapter. Read it. I go to it first, to be honest with you. Very, very nice. There's an overview, reinforced embankments, fills, retaining walls, and then finally berms. But just beautifully done from a practitioner, somebody who's done it. So very, very nice. This is an expanse anywhere you need a break and grade reinforcement. The general public sees this wall, has no idea the geosynthetic is behind it. None. Just they're lost. They see the front face and that's all they believe. But it is a structure, and that reinforcement element is critical, as well as the drainage component of it. This is the retaining wall. This is the anatomy of the retaining wall. You have reinforced soil as well as retained soil. You have a back as well as a base drain. The interaction between the facing element and the reinforcement is critical, and that you have long-term drainage is critical. The design for this is very straightforward, and it goes through the series of sliding, overturning, bearing capacity, spacing of the reinforcement elements, and then anchorage of the materials. Can use a textile or a grid in this application. The grids are used because of the strike-through of the material, but Chris beautifully goes through the rationale for these different materials as well as that design, and it's rather straightforward. The anchorage is critical, and the connections is critical. And to mobilize the reinforcement strength, you get overzealous. You can make reinforcement tremendous capacity, but can you translate that to the facing element or through the reinforcement is critical. Students are in here. Do you do this design by hand any longer? No. The old guys, yeah, we did it. But your computer programs are available. But you have to look for who is it from. Okay, it's from the manufacturer. Obviously, they're selling a product. Okay, could be public or private. The public, particularly in the U.S., we call them cowboys. Okay, What is the big cost of a wall? It's the reinforcement. It's the backfill. So the backfill is where the savings are. Okay? And this is where the public versus private comes in, the quality of the backfill that's used in the wall. The public is typically the agencies like the DOT, the Department of Transportation. The private is typically for the US, it's a big box store. I don't know if IKEA or what does, but if they need a retaining wall, it's designed very differently. Okay, we also have state and federal codes that are out there, but these codes are available now. And the future of the IGS handbook is to have computer codes with it. So that is on the horizon, to marry those things, to never print it. I'm glad you did. It's beautifully done. It's better than the original, to be honest with you. And it'll be available with computer programs going forward. Changing now from retaining walls to embankments. Certainly this is an application that's very familiar to you. Off of a barge and the reinforcement, PET geotextile in this application, being stretched into confining areas and then backfilled through a dredge. You see the turn that they made down the river. Subsequently, prefabricated vertical drains through it. And there we have it. We took a page out of your lessons. We learned from you well, and we constructed land. So this is very close to my hometown. The design of this, Chris does a beautiful job in this regard of making checklists that he goes through. And these checklists are highlighted by the design areas which are in red. Okay? So the first is bearing capacity. The second one is a global stability failure, very classic through the reinforcement. The next is the elastic deformation that's associated with this. Subsequently, anchorage pullout from one side of the embankment versus the other. And then the lateral spreading, how much deflection are you going to have at the crest? But Chris marches through this just beautifully in the text, and he did yeoman's work in this regard. You can superimpose on that, which is the first learnings. So how about now you go to embankments over columns? And these are typically aggregate-filled columns that are surrounded by geosynthetics. Just wonderful. I could read it over and over again. It's wonderfully done and a classic move. Kent, I've never presented in front of somebody, the author, but this is a family friend, and you did very well with your chapter. You'll see the superposition of Rowe's work versus Montmaubert's work, which are extremely different written. Just radically different. And Kent followed the rules, so to speak, in making it practical and making it very nice. Think of his chapter, though, with containment of water. Okay? There's where the primary difference is, water to waste. Okay? Rowe's section is containment, particularly for waste applications. Kent took after, he goes from dams to canals to reservoirs to transmission of water. It's very well written in the chapter. Design considerations, installation, but I'll show you specifically where his power is. And it's in regards to the installation and quality assurance, quality control. This is where the real value of this chapter is. It's in the tail end section, and then he goes into sustainability, which is nicely done. Okay, two types that he concentrates on, geomembranes and geosynthetic clay liners. He breaks them down into two trains as far as the containment material is concerned, and he goes to first principles of manufacturing. Dams, dam facing is covered, ponds, and even to reservoirs, size difference, one agriculture, the next, water containment, canals, transmission or conveyance systems. These two diagrams you should concentrate on. This is important, or consideration concerns, and this circular discussion will be by many of the presenters in the next, the tail end of the afternoon. But this is right on target as where we're moving with these things going forward. This is also a checklist of important seepage control and sort of the steps you should follow in that regard. And very nicely done. My hat's off to you. The next section, though, particularly with the photos, are learned from the other people's mistakes. Okay? He was very generous with this and can only be gained by somebody who's actually done it in the field. This work, he's very kind with the photographs. You can manufacture the nicest geosynthetics out there, but if you don't do shipping and handling properly, if you don't have an installer who knows has the right equipment, if you pierce or lance this material, it's not steel blasting mat, but it certainly needs a protocol as far as installing it, and it needs to be checked after it's installed. So, well done. Your chapter is very nicely done. We then break radically from that and move to Professor Rowe's chapter. This is on waste containment, again, as a barrier, but now waste containment. And Professor Rowe departed radically from this. He's at Queen's University in Canada and really focused on a lot of his research. And the idea is what goes into minimization of liquids across the barrier, and what are the key elements for that. And Professor Rowe addressed that in these different applications of landfill, mining, impoundments, and then remediation sites. So those 4 areas he looks at in depth. What are we in the business of? And please realize we're in the business of minimization of leakage. That is the key element, and it has to be superimposed over the long term. Professor Rowe said, can do it short term, no problem. But can you do this for the long period of time, the long haul? And that's critically important. He says siting of these facilities has to go through a protocol, and this is what he presents. These facilities are massive. Latin America in particular, for mining applications, the cost of metals is through the roof, and these projects are just getting bigger and bigger as we sit here. The first one is solute flux across a barrier. Can you change the polymer makeup of a geomembrane, a polymeric geomembrane, to stop this migration? Of course, you can change the density. Density is definitely related to crystallinity. The higher the crystallinity, the less the solute flux. You can change from a monimodal to a bimodal resin. You can incorporate an EVOH layer or a vinyl alcohol layer into the material. You can change the thickness of the material. It's a lot of different items that you have at your purview to change the solute flux across the material. You also are very interested in durability. Most of these facilities have a 100-year design life plus. How do you assure that over time? And this is typically done off of time temperature superposition and Arrhenius modeling. You need some sort of accelerated test. That accelerated test is typically run at 3 or 4 temperatures. You're assuming that the elevated temperature is degrading the material over time. You subsequently will take the half-life of that and predict how long the material will last from the slope of the Arrhenius plot. You then take these laboratory results and superimpose them on your field conditions. So you need field data, and this is how that is done. You have antioxidant depletion, induction time, and then half-life is what you just saw. You see the lifetime prediction for HDPE, and then you superimpose that versus field temperatures to get how long it will actually last. Yeah, that's a big ask for a graduate student, but they've done it often. He's also very concerned about continuity of the material. Okay, you cannot have these materials punctured and have them, stop the migration of flow. So puncturing of the material is forbidden, and you have to protect these barriers from puncture. This has not always been the case in the field, and we know that because of the leakage rates and the detection systems. Work from leak integrity surveys are showing that aggregate and gravel, which is placed for the leachate collection and removal system, is the problematic actor here. You have to have a big puncture protection material over top of a geomembrane to stop it from puncturing. There are tests for this which have been developed in SEN for detection of this. This is one of the many. They then argue about considerably the amount of deflection that you can have in the geomembrane. 3% seems to be the number, both here in the EU as well as in Britain. This is quite a bit less than the yield strength of the material, which is typically up in the neighborhood of 12 to 16%. Rowe, as well as Fadi Abdullah, Richard Brockman, have done long-term performance tests in these cells. They've showed that once you age or embrittle the material, you can rupture it quite readily. So you're very interested in the durability of the material, keeping it flexible over time. Flexibility is probably more important than strength. This is a paper from G&G, which they proved that to, and then the final results from it. The leakage rate, the last item that I'll cover, is how powerful it is to have a polymeric material underlined by a natural material, being it a compacted clay liner or a GCL. Here you see the power of that in the leachate height versus the intimate contact of the material, the pressed fit of the geomembrane against the compacted clay. This is problematic. Those whales or those bubbles in the geomembrane are unacceptable. Okay? You must have a pressed fit of the geomembrane against that clay or GCL. How do you do that? He gives a listing for that. There are techniques for it. You can incorporate a scrim in the geomembrane to stop it from thermal coefficient of expansion and contraction, but there are different avenues to do that. Got to keep it small, though. You're not going out there and laying many hectares of facility all at once. Okay, the last chapter of this is again authored by me, and this chapter says it takes a family. Okay, It takes all of us in the room to make this work. It gives different avenues of the stakeholders. I'm glad you used that word in your introduction, of the players, so to speak, for the facility. It also critically looks at the quality system approach to any of these facilities. A good material, okay? You need it to be quality assurance. You need to have it installed by a certified installer. You need to have it inspected, okay? We're all better when we're checked. Performance tested, like leak integrity survey, and then subsequently to that, there is operation and maintenance associated with this. It's actually an honor and a privilege to be with you. I thank you so much for the opportunity. This is the summary slide, which you're looking for. I think the standard of practice is very good for geosynthetics. I think we've come a long way in 50, 60 years, but still there's a long way to go. Testing and design counterpoints nicely into this functional approach. Applications are certainly increasing. I started that in the beginning of the day. Emphasis on durability, sustainability, and cost effectiveness. I think you'll see that in the afternoon discussion. This emphasis on the quality system approach. I've said it now 3 times. It's probably the most important thing that I'll leave you with. Geosynthetics will play a bigger role in civil construction going forward, and I certainly think they're underutilized. We are just starting. It's a great business to be in. Thank you so much for the invitation, and I'm on time.
When I first saw his presentation of 120 slides, I said, well, are you really able to do that in 3/4 of an hour? But it was the case. Are there any questions? Then they can be raised now to George. Later, at the end of the afternoon, you can also raise questions. But if you want, it seems to be clear for everyone, as always.
The book is... It was really an honor. It's a real privilege to ask these people. Everybody's busy, but certainly to write it. And please realize it's a living document. We take corrective criticism well. If there's something you don't like, tell us. It's made to change. If we've left something out, we take no umbrage. It's truly a living document. It's not a record. So we know there's things in there. Certainly.
I don't know if you want to use that one, but I'm a geochemist, so a little bit outside the scope of this talk, but you are hinting about active barriers and reactive barriers. So what is your experience with reactive barriers?
From 2 sides. The question is in regards to the reactive barrier. If it's punctured, if the barrier is punctured, will it self-heal? This is primarily from the GCL component of it. A big issue is, what are you trying to contain? This is different between water, polar, salt water, and now you can change the montmorillonite or the bentonite with polymer additives to target a specific leachate.
Is it in the book?
It's in the book, yeah. Yeah, there's more coming, though. There's a lot more coming. There's even a difference in regards to different polymers which can do this, and self-healing of polymers themselves. Some of the asphaltic materials are leaning in this direction. There is a price, though. And you do have to know the environmental conditions, and not just the leachate, but also the temperature regimes. A big push, both in South Africa and Australia, from brine applications. And now the big one comes in regards to metals, particularly from the standpoint of gold. So you can imagine when you're gold mining with cyanide, it really matters, and the pay is there quite well too. Now change your mind totally from the chemistry standpoint, but now shift into construction. They're now developing like Gore-Tex, breathable materials, designs with vents, designs that are undulated. You see, just in this room, most rooms are not curved. It costs to make this curved, but how nice is that for the people in the back to do that? But these things are being incorporated into the construction, and you have to work with the architects and the engineers to do that. But from two perspectives. One is from the chemistry side of things, but the other is from the design, the architectural side of things. Great question. Certainly.
In one of the slides, I remember you said that...
One moment, we have the box. I hope it works. It works? Yeah. Yeah.
Cool. I like that. That's neat. Yeah, I never seen that.
I remember you said we could trade off the strength a bit for flexibility in the geotextile, but how much of the strength are we willing to let go of in favor for flexibility?
Oh, gosh, I like you so much. This is a beautiful question. Thank you. Let's look just at polyethylene, okay? So you have to know the load deflection, the stress strain curve for the material to answer this. And then there's a strain compatibility with the soil that you're interacting. But for HDPE, for instance, there's a yield and a break. So the stress strain, the yield strength is around 12 to 16%. Okay? How much deflection are you anticipating? Well, if you're in the Shield, you're meters of deflection. That's a lot different. The strains are very high, but usually we're in strains 1-2%. So how far up the curve do I need to go? So it very much depends on the environment, and that's where the engineering comes into play. It's a beautiful question, and that compatibility with how much can you tolerate. Is it temporary or is it permanent? I have some walls that walk half a meter. You know, my structural friends, that's not right. That's not acting that much movement. So.
Yes, I have a practical question. We decided to publish it in as a printed version, and you said in several sentences that you want to have it as a living document. How will it be handled in the future? Now we have this printed version. Will there be updates to add it to the book, or you cannot always print a new book? So my question is, will it be available online, or what is your idea behind it?
I was told it would never be printed. Mm-hmm. When I signed up for it, I thought it would only be electronic. Yeah, all the subscribers are privileged to a life of the document through electronic version. I never anticipated to see a printed version of it. And I know this is under review. They're having an entire changing of the guards. In Montreal will be the 13th International Conference. They will change and they're already assigning new authors for this, and it will be an electronic. But going forward, you should anticipate it only electronic version.
Okay, thank you.
And it should be public access too. We want it for promotion. It does us all good. So great question.
Anyone else?
In the Netherlands, there's also some discussion about using high-quality products such as polypropylene for usage that is quite short, such as vertical drying drainage. Is this also a discussion that is ongoing in the United States, and what is your opinion about that?
Oh, now this is a big issue. Using first quality polymer, recycled polymer, is that your, or?
For instance, there are multiple products, but there is a lot of discussion here about, especially with CE, you have only limited recycled products, and vertical drainage, you only need it for months.
Yeah,
Sometimes shorter.
You're on it. So let's superimpose the different items and the pros and cons. That durability, that 200 years. Am I going to do that with a non-traceable polymer? Am I going to put my stamp on that I have a long-term AO package and that it's consistent across the material with recycled, reclaimed, or reworked material? Reinforcement barrier, I probably have trepidation. I probably have pause with that. Why not use those materials in a drainage application? Yes. You know, if it would fracture or break, it would still have the 3 dimensions that you would have flow. Applications, temporary versus permanent. Yeah, I love that question. You have to work with me, though, on it. You have to choose right, and you have to be upfront. You have to be transparent. And I was just in Lubeck with Naue. The traceability is all the way back to the polymer. They know where that is from a barcode. You can tell, you know, on a job site. So that's critically important. And I didn't touch much on it, but Ro's work is very nice, from stabilization through the production, and then you go out into the field through durability with that additive package. It's not only important from the base resin, but from the master batch as well. Very, very good.
May I add something to that? Can you hear me? Yes. There is already a vertical drain, more than 20 years, on the market, used quite a lot, which is built and made of recycled polymers. We never published that in the past because that was not a sales argument. But nowadays, it's a very well use of recycled polymers. So addressing to that, yes, those products are there and working perfectly. And you have to develop a special method to make the core, but that is there. So those things are, nowadays there are so many designs going on using the recycled polymers that we are running into the problem that we can't buy enough recycled material. But that's another story, and I will address that later.
There are also fully biodegradable quick drains available on the market.
Yep.
They're still used in small projects, but especially in this application, it makes sense to have something which is fully biodegradable.
And then on the other side of the spectrum, you might want it long term so that it adds reinforcement to the section. Not if it wrinkles, but depending on how much settlement is there as well. So 2 different sides. Excellent. Excellent. Love the discussion.
Yes. I interpreted the question before a little bit different, in the sense that when you have vertical drainage and after 1 year you start building the road or whatever, in the Netherlands for instance, you don't want that drainage function be there anyway, because the road is already ready. You don't want to sink it lower. Anyway, so after 1 year, we would like to have the drainage gone, like no more traceable, and that's biodegradable plastic then. But that is not allowed within the standards at this moment. And that was my interpretation of the question. How do you working that in the US? Is there some going on, or?
Oh yes, typically adding a starch to break the material. The unfortunate, or the thing that you don't have it degrade uniformly, and it's tough to degrade some of them. We build them too strong. You dig them up afterwards and they're still there. You said that it was going to degrade and it didn't. It didn't uniformly degrade. So yeah, they're trying now to put accelerants down into them, and nobody wants that. So it's a struggle. Trying to do it with electricity. Put a carbon black strip in the back of it and introduce electricity, so you have osmosis going on with the degradation of the material. Carbon black loads have to be up around high teens into the 20%.
One comment to the last comment. I think the construction production regulation as we have in Europe is valid for products that are static, relevant for long term. And I think this is not the case when you have a product which is only needed for a year. So CE is not a requirement for these kind of products.
Great.
Okay, I think we stopped discussion here. 5 minutes break and then we continue. And if you are, still coming up with certain questions for George, you can always raise the questions in the panel session. So 5-minute break till, 2 o'clock. Thank you, George.
Yeah, you're kind.